like Dominican. I'm every day, I've got the panicking. I pull for my phantom.
Just had to make sure that everybody saw my 97s. Know there's been a lot of talk about my crusty Air Force One. Thank you, Chiffon, for the song suggestion. That was just an extra shot for good measure. And now it's time to talk about resistivity, conductivity, and electrical potential. The first header in your notes should be resistivity and conductivity. So yesterday when we talked about Ohm's law, sorry, my neighbor is just standing out there, staring at me. Really can't blame him, Physics is awfully fascinating. Anyway, so yesterday we introduced this idea of resistance when we were talking about Ohm's law. So we have this equation, right? V equals IR. V is the voltage, I is the current, and then R is the resistance, which is essentially just how much your circuit is going to resist the flow of electrons, right? So let's take a closer look at resistance. If we isolate resistance in this equation, we get R equals V over I. So you might be thinking, okay, well, if we want to increase the resistance, can't we just change the voltage, right? When we just want to increase the voltage, because we see that those two are actually directly proportional. However, changing the voltage will not actually change the resistance. When you make a circuit out of what we call an ohmic material, it's going to maintain a constant resistance regardless of whatever your voltage or current are. So that's kind of like your set value, right? So I'll say that again. Ohmic materials maintain a constant resistance regardless of what voltage or current you use. So in order to change the resistance in your circuit, you actually have to change something about the resistor itself. So we're going to look at some different characteristics of resistors now. So let's say we have this cylindrical resistor here, just to keep things straightforward. And so the first thing that we're going to think about is the material that the resistor is made out of, right? Because we know that some materials are considered conductors, some are considered insulators, and then in between we have semiconductors. Okay, so we have this little symbol. It's called rho. It kind of looks like a wonky P, but it essentially just stands for resistivity. And each specific material is going to have its own value for resistivity. So, as you may guess, if you have a higher rho, a higher resistivity, you have more resistance. So, something like copper has a resistivity of 1.68 times 10 to the negative 8. And then something like rubber, right, an insulator, not a conductor, has a resistivity of 10 to the 13 approximately. So that's a huge variation, right? We also think about two other aspects when we're thinking about the resistance of a given resistor, right? So we have the materials, that's set. But you can also increase the resistance somewhat intuitively by increasing the length. So if we have a greater length for our resistor, then we have more resistance. And then there's also the cross-sectional area. So if you see here in this diagram, right, that kind of side face of that cylinder is going to be the cross-sectional area. And if you have a greater cross-sectional area, then there's more room for that current to flow through. It's kind of like what we were talking about yesterday with the bottleneck versus just like a regular open cup, which is harder to pour something out of. So if we increase the cross-sectional area, we actually decrease the resistance of our resistor. So now that we have all of this information, we have an idea of what these relationships look like. Let's try to figure out how our equation is going to look. So how do we calculate the resistance of a resistor? So we know that length and resistance are going to be directly proportional. So length is going to go on the top, right? That's going to be in the numerator. And then we know that area, A, and the resistance are inversely related, right? They're actually inversely proportional. So A is going to be in the denominator. And then we also multiply this ratio by the resistivity of the given material. So we end up with this full equation here. Now that we've done all of this thinking to define resistivity, it's actually fairly easy to start to think about conductivity. So we think about resistivity as how much something naturally resists current. Resistivity is just how much something naturally resists current. And then conductivity, on the other hand, is how much something naturally allows current. So we represent conductivity with the sign sigma. So sigma represents electrical conductivity. And it really is this easy. Resistivity is just equal to 1 over conductivity. So they're just inverses of each other, right? So alternatively, conductivity is going to be equal to the inverse of the resistivity. Essentially, a great conductor is going to be a terrible resistor and vice versa. The last thing that I want to do today is expand on this idea of voltage and what exactly it means to say that we have a certain voltage in a circuit. So we talked yesterday about this idea of electric potential being the amount of potential energy per unit charge at a specific location. But when we talk about the voltage in a circuit, we actually think about this idea of electric potential difference. And I'm going to expand on that a little more. So let's imagine that we have this electric field here, and we want to move this charge against our electric field from point A to point B. Well, that's going to require work to be done on that charge by an external force. So you need external work being done. And then when we think about the difference in electric potential from location A to location B, this is actually called electric potential difference, so the change in V. So we define electric potential difference as the difference in electric potential V between the final initial location when work is done upon a charge to change its potential energy. So we think about 1 volt as 1 joule per coulomb, or we think about voltage as the electric potential energy per charge. So I'm actually going to use a specific example to kind of make this point a little more clear. So let's say that we have a simple circuit, and in that circuit we have a light bulb and we have a battery that has a voltage of 12 volts, right? So we have a 12-volt battery. This means that every coulomb of charge is gaining 12 joules of potential energy as it moves through the battery. And also, at the same time, right, every coulomb of charge is losing 12 joules of charge as it moves through the external circuit. So what I mean by that is we're losing these 12 joules of charge in order to light up the light bulb in this specific example. So the loss of this potential energy is resulting directly in a gain of light energy or thermal energy or whatever form of non-electrical energy, depending on how your circuit is being used.